Alright, so some of this stuff I just went over with you. Alright. One thing that's you also find on the periodic table is what's called the atomic weight, which is actually different than the atomic mass unit. So as it says, the atomic weight is it's an average of all the different isotopes. So for example, well, not all, it's all the different isotopes that are found on the Earth. And, predominantly most of the Earth we find hydrogen 1, so it's not surprising that the weight is much closer to 1 than it is 3, for example. For different elements, here, let's take a quick look at an example. So on the Earth, we have, most of the atmosphere, for example, is made of nitrogen 14, right? Nitrogen is element 7, so that nitrogen 14 has 7. 14 minus 7 would be 7 neutrons. And then there's so that's like 99.63%, and then there's a small number of nitrogen atoms that are actually nitrogen 15, so they would have 8 neutrons in them. Chemically they act exactly the same. All right, so when we look on the periodic table and you see the atomic weight, it's going to be much closer to nitrogen 14. So how do we calculate that? You have to use this thing called the atomic mass unit, or sometimes it's U, and those numbers are always going to be given to you when you do this calculation. I think I have one in the homework. So basically you turn the percentage into a number, move the decimal place 2 places to the left, and then multiply it times the weight of whatever isotope you're talking about. So for example, nitrogen 14, you'd be given this number again. So this times this plus the percentage of nitrogen 15. So in numerical terms, you got to move the decimal place 2 places to the left. So it would be, see how small this is, 0.0037 times the atomic mass unit, or the U, of nitrogen 15, which again, this number is given to you, the percentage is given to you. So you multiply the percentage times the AMU of the isotope, and then add it to the percentage times the weight, the AMU of the other isotope, or however many isotopes you have. This was an example with just 2. Sometimes there's 3, sometimes there's even 4, and so on. All right, so it's a very simple calculation, and that's what you find on the periodic table. All right, so let's see. Now let's turn to what's called the classical atom, and we're about to go into the realm, just to let you know, the realm of what's called quantum mechanics. Quantum mechanics describes what's happening inside of the atom. Particularly, quantum mechanics deals with what the electrons and the light, the photons of light, are, how they're interacting with each other. So in the classical theory, like if we just take what we knew from Isaac Newton, and we know from electricity and magnetism, it turns out you can't build atoms, at least not real ones that are part of this universe. So here. So let's take a look at it. So electrons. The first thing, and this is not right, okay, just understand that electrons, people imagine orbiting the nucleus. For example, the way planets orbit a star, like the Earth orbits the Sun. That's completely wrong, and we're going to see why. Because if the electron is in a curved path, it would constantly be undergoing acceleration. And from electricity and magnetism, what we know about electricity and magnetism, if you have a charge, which that's exactly what an electron is, if it was accelerated, it would radiate. And if it was radiating, it would be losing energy in a constant manner. And so, like, if you imagine, some tiny positive charge, I'm not going to really do justice to this, but let's say there's an electron in orbit around this. Okay, so there's an electron somewhere out here. It's supposed to be a circle, but you get the idea. So what would happen is as this thing is undergoing acceleration, because we know that from mechanics, all things that are moving in a circle are undergoing acceleration towards the center. So there's an acceleration in this direction according to classical mechanics. And so what would happen is, rather than stay in some stable orbit the way the planets do around the sun, for example, or around another star, what the electron would do is it would, in just less than a second, as a matter of fact, it would begin to spiral. It would spiral in towards the nucleus and ultimately crash into the nucleus. Okay, so this is what this example here is what classical mechanics tells us is going to happen, or happens, to electrons. Okay, so let's go back to the PowerPoint, and of course that so the electrons would continuously lose energy. Oh, I didn't really show. Here, let me go back to this picture for just a second. One of the things that I'm not showing here is as the electron spiraled, it would give off photons of energy. Basically different colors, in fact. Not E, sorry. Photon. A photon. P. Anyhow, it did different colors. I should actually be using different colors. But anyhow, that's not at all what is observed. That's not what happens. All right. So that's what this says. It would lose energy, and basically atoms as we know them would not exist. So we needed a new theory. And what I'm going to do is we're going to build up towards quantum mechanics. It took a while. So this is the beginning of the 20th century, early 1900s. In 1900, you might recall from chapter 7, we came up with this formula, or we didn't. Max Planck did. He won a Nobel Prize, of course, for this. And it says that energy of a photon is a constant times the frequency of the photon. Okay. In 1905, Einstein came up with another formula using this idea to explain the photoelectric effect, that photons or particles of light are quantized. And he won a Nobel Prize for that. Just to kind of go back, if you had white light, which is composed of all the colors of the rainbow, this actually is a demonstration of that. So the white light goes through a thin slit. The slit encounters a prism. Nowadays, of course, we hardly ever use prisms. We use what's called diffraction grating, but it does the same thing. The different colors of the light are different wavelengths, or also known as different frequencies, right? Depending on how you look at it. The shortest wavelength is the blue light. The longest wavelength is the red light. And in this prism, or in diffraction grating, the blue light gets bent more than the red light, because the blue light has a shorter wavelength, and the red light has a longer wavelength, so it's not as affected. And so anytime you have what's called a continuous spectrum, that is coming from, white light, or something that is giving off its own light. That's called black body radiation. We mentioned that a little bit in chapter 7. All right, that's not really what we're going to concentrate on, however. Now, here's an interesting experiment that began in the 1850s, believe it or not, all the way back to the 1850s. Basically, what we did is put different elements in a glass tube and sealed that tube. So we put hydrogen in the tube, we put oxygen in the tube, and if you put a voltage across this, it's a wonderful demonstration. You put a voltage across it, and you pass it through a prism, or like this prism and slit gets replaced by what's called diffraction grating. You get only certain lines. You don't get this, the continuous spectrum of black body radiation. You get certain lines and not other lines. In other words, certain colors and not other colors. And like I said, we knew this as far back as the 1850s. In fact, one of them was called the Balmer series for hydrogen. When hydrogen was in this tube, it created a certain pattern of colors. There was a red line. There was actually another red line. There was two red lines, kind of close together, and then there was an aqua line, and then there was a blue line. And they're very specific wavelengths that are measured, and it turned out that nothing else produced that exact pattern. Okay, so in fact, this is how when we put hydrogen in here, and then we get that pattern of colors. When we look in our telescopes and do the exact same experiment in our telescopes, we see the same pattern, and so we know that, for example, the stars have hydrogen in them, and then the other elements as well. So this spectrum is particular to each atom. Each atom has its own spectrum. It's kind of like the fingerprints of the atom. Hydrogen has its own. Helium has its own. In fact, helium wasn't really known here on Earth. And when we turned the telescopes to the sun, our telescope to the sun, we found this new pattern, a completely new pattern that was not in gaseous form on the Earth, at least not in a way that we had trapped at that time. And so they, in fact, since it was the sun, they named it helium. Helios is the Greek. I think it's Greek or it's Latin. I don't know. For the sun. I think it's Greek. All right. So now we come to the year 1913. All right. So remember, we're leading to quantum mechanics. So Niels Bohr gave us a giant step forward in explaining the Balmer series, right? This Balmer series for hydrogen. All right, and so here's what he said. He came up with these three rules: that the electrons only exist in certain allowed orbits. Later on, we're going to call these orbitals because they're not truly orbits the way a star goes around the sun. So there's only certain allowed ones, and we're going to find out why that is as well. Within the orbit or orbital, the electron doesn't radiate. So even though it's going around the nucleus, it is not undergoing radiation. And then when does radiation take place? Radiation is emitted when the electron jumps from a higher orbital to a lower orbital. And so it has less energy, and so that energy goes off as a photon of light. And so Bohr is the one who came up with that idea.